Okay, so I'm going to be talking about a new substructural logic for inconsistent mathematics, and this is joint work with my PhD supervisor, Zach Weber, from New Zealand, and it should be fun. Okay, let's start. So what's the motivation for this kind of work? Well, the motivation comes from inconsistent mathematics, and the topic of inconsistent mathematics is essentially inconsistent structures. What do I mean by an inconsistent structure? There is a big difference between what people like Zach Weber or some other folks mean by these kind of things and what, let's say, Graham Priest means by these kind of things. For instance, what Thomas presented the other day here, all of those models, we wouldn't take them to be inconsistent structures because they are actually classical, fully classical structures. Nothing weird about them. On the other hand, an inconsistent structure would be something that arises in the setting of an inconsistent theory. Okay. Of course, it is well known that inconsistent theories, according to traditional wisdom from classical logic, are all categorical because there is no model. So trivially, almost are isomorphic. So there isn't much interest in studying these sort of things, inconsistent structure, inconsistent theories, and so on, where you would find these sort of inconsistent structures. However, some people realize that in fact there is a way to make sense of these creatures, of these inconsistent theories, and so on. And well, some of those have already been mentioned, I guess, and surprisingly, it was shown that in particular for something very important, which is naive set theory, there were ways to make sense of that theory, even though traditionally collapses into triviality, right? So there were non-trivial models of the theory. And this sort of work was essentially done by people like Ross Brady, and Graham Priest, Morado-Estrada, etc. And yeah, so the idea was to use preconsistent logic to make sense of this, and somehow you can build structures where you can get models for naive set theory, even though the theory itself is just inconsistent. Okay, so Da Costa, he's got some sort of motivation for exploring the world of inconsistent mathematics. He says, well, it would be interesting to study inconsistent systems as, for instance, the non-Euclidean geometries. We will obtain a better idea of the nature of the paradoxes, could have a better insight on the connections amongst the various logical principles necessary to obtain determinate results, etc. It is our aim to eliminate the inconsistencies. But it is not our aim to eliminate the inconsistencies, but to analyze and study them. So the idea is somehow to explore this new world of mathematics, essentially. And it's not such a crazy idea if you think about it for a second. For instance, John Bauweiss, one way he found to motivate work in abstract model theory, which is a generalization of model theory, was saying something like, well, look, if you look at real analysis, if people had just stayed studying the things that happen in the particular domain of the real numbers and not try to look at more general polynomial functions and so on, then the understanding we've got today of real analysis would be incredibly different. Right? It's always good when you take a step back and you look at a more general concept. And in this case, a concept would be something like mathematics. Okay, why does it have to be consistent? Why does it have to be classical? What happens if we just take a step back and we look at a more general notion of mathematics, where you can also include these sort of inconsistent creatures, right? And of course, you have to do that from a different perspective from the traditional, let's say, ZFC or whatever. You need to go into some theory that will allow you to build these sort of creatures. Okay? In particular, let's say naive set theory is a good idea. So the program has had two main themes, essentially recapture and expansion. So by recapture, we mean, well, we want to be able to present this to mathematicians and allow them to recognize something that they're actually doing, right? So we want to be able to say to mathematicians, look, In fact, what you are doing here is something that you could also do in this other setting. At least many interesting things that you are already doing here in classical logic, you could do it in this setting as well. And that will be certainly good for motivational purposes at least. And of course, expansion, because once you have these new structures into consideration, once you can say something like, for instance, you've got some domain, and in that domain there is some element that lives in there, and at the same time it doesn't live in there, or maybe the domain has one cardinality, it's maybe finite, but at the same time, every possible cardinality embeds into that domain, right? All sorts of crazy things can happen depending on how you set things up in the setting of these naive set theories. So that's interesting, and that would certainly extend our understanding of what a mathematical structure would normally look like. Okay. For instance, to give you a simple example, if you consider that if you allow for these sort of inconsistent structures in the setting of naive set theory or whatnot, you can find a structure in which you can interpret your language such that the structure has cardinality 1 and every sentence is true in that structure. Every sentence with certain restrictions, right? Where there is no button involved or something like that, right? So there are certain restrictions, but let's say every sentence of a language such as LP would be true in this structure, and not true in a sort of weird classical sense like the LP semantics does, right? But actually true. If you lay down the truth conditions for a language using this theory, you will obtain that every sentence of the language of LP would be true in this one element structure, which means that the Leuwenheim-Schkolem theorem is automatically kind of trivial, right? You get these sort of weird, interesting results. And then, yeah, so that's part of the expansion part of the program, essentially. So, okay, let's see what else we have. Okay, yes, and of course, in order to be able to accomplish this, you need to have some logic that will allow you to reason in this setting and, let's say, build a model theory or build a proof theory or whatever you want to do using this new set theory, this naive set theory. And in particular, the logic has to satisfy certain requirements, more or less. All right? First of all, it has to be weak enough to support large abstraction schemes, such as the set comprehension axiom without triviality. That is, we want something that won't bring disaster about, right? So you shouldn't be able to get Curries paradox or anything like that. That's one of the requirements. On the other hand, it has to be strong enough to be able to support actual proofs, okay, and try to reconstruct familiar results. This is the desiderata, essentially. And for instance, in the case of LP, it doesn't seem to be the case that it's strong enough. For reasons that might be familiar, right? It doesn't touch. That's pretty horrible. And I mean, it's even worse than that, because there is this paper, well, by Thomas Foster, and they show that in fact you cannot even define a connective that will have that property, the detachment property, and it's a bit of an interpolation result. So that's pretty horrible news for LP, I would say. So then the aim of this talk is essentially to propose a logic that has been used by Weber, and I've collaborated with him on that, to basically do this. And we wrote a paper that was published in the AJP, where we tried to do some basic meta theory, let's say, for a restricted fragment of the language we were using, right? Essentially, we did some meta theory for the language of LP within a logic that contained that other language, right? But we didn't assume any. There was no distinction between the logic we were looking at and the logic we were using in the meta theory. At least at the restricted level of the connective, having to do with conjunction, disjunction, and negation. So, and all of that using naive set theory. Okay. So you have to reason in that way. And in particular, one of the obstacles of this sort of project is that many times you don't realize how entrenched your classical intuitions are. And you try to reason using these non-classical logics in the way you would do in traditional mathematics, and you sometimes believe that something you proved is actually correct and that it is fully non-classical. And it turns out that there was a hidden classical assumption that you didn't realize. And many of the results collapse. So probably, if you're a PhD student, I don't know if I would advise this. I would probably leave this for people who are already on the TV track or something. I certainly, that's what I've said to my former supervisor that I would do. I will try to publish because that's more pressing right now. But yes, it's really interesting topic, and I reckon that it's absolutely fascinating. And but certainly it will require a lot of time, and it requires that you sort of take off your classical suit and put on a completely new kind of clothing that will allow you to reason in a way that most people normally don't. So yeah, pretty insane. So okay, so what do we want? First of all, we want an effective conditional, a conditional that obeys certain properties. First of all, we want the conditional to detach. We don't want the material conditional, because of course, otherwise we would get the disjunctive syllogism, and as you might know, that quickly leads to explosion. So that's something we want to stay clear of. And we don't want the conditional to obey contraction. That's another thing. Okay? We want to avoid contraction because of Curries reasons. The conditional has to either contrapose or weaken, but not both. Unfortunately, when you have something that contraposes and weakens, you quickly get explosion. If contraposes, weakens, and you have some negation principles, yes, you quickly get explosion. Yep.
I just want to ask about the sort of positive part of this consider on that you want one or the other. That's just sort of because you want as much strength as you can get without running into trouble?
Yes, yeah, that's it. That's it. Yeah. And well, in case you want to know why this is, I mean, it's a pretty straightforward proof, right? So you want to show this, so it suffices, let's say that you start with this and this, right? And then by weakening, you get what? That this is principle, right? B and A, right? So this is going to be a principle. So from this, I can get a not A implies actually that B implies A, but then contrapose this, and then we get a not A implies that not A implies not B, right? And then well, just detach here, and then you get A not A implies not B, right? But then if you've got like that negation eliminations and some other stuff, everything follows from that. But even if you get that every negation is probable, that's silly. So I would stay clear from that as well. So that's why you don't, you cannot have those two things here. Of course, you need to have a reasonable introduction rule. Plus, if you are looking at the Hilbert-Stein system, you wanna have a deduction theorem, which is not. Let's say in a traditional contractionless setting, the deduction theorem takes the form of a local deduction theorem. That means that you have a connective that residuates. If you have a connective that residuates the implication, that will essentially mean that if this happens, then you only get as a theorem the, well, let's say, some iteration of A's, probably the way to actually write this is just A to the n implies B. And that means this A to the n is just some iteration of A using the connective that residuates this implication. That's what happens in a traditional sense. So this is something that you would, ideally, you would want to define some consequence relation if you're looking at the Hilbert system, such that this deduction theorem would take a more natural form. This form is not incredibly natural. Certainly, this is not the form you would see in mathematics by any means. But again, it's the reason why this happens is because this consequence relation in the Hilbert system is not defined in the appropriate way. So we are going to show you how to do that in such a way that you get an actual deduction field. But yes. So, okay. And of course, support the theory of identity compatible with the axiom of extensionality, and that's related also to Grishin's paradox and stuff like that, right? So, because if you have too much substitution, then you get into trouble, you get contraction back, and it's a disaster with extensionality. Okay. On the other hand, we need negation to have a bunch of properties as well. First of all, either exclusive or exhaustive, but not both. Okay. On the other hand, you don't want to get explosion. That's something that we want to avoid, of course. Support argument by cases. This is something that you want to keep because, in fact, argument by cases is used pervasively in mathematics. So if you don't have that, it's like pretty terrible. On the other hand, you do want to keep reductio ad absurdum arguments. And what I mean by that, well, I mean, what Zach Weber means by that is essentially this. You want to be able to, well, if this happens, you want to be able to conclude that, well, in fact, not A. Okay? So that's essentially what we in these pages mean by that. So on the other hand, you want to have full De Morgan properties. So that's well known, right? Negation, duality between conjunction and disjunction, so and then yeah, of course. So one of the most basic reasons for these demands, of course, is because since we are looking at, let's say, the setting of naive set theory or something like that, you will get contradictions within that theory. So you need to be able to deal with those contradictions without falling into absurdity. Okay, so there is a small problem here. That on the one hand, we are demanding that conjunction that we want to have in our logic to have some properties that make it essentially a multiplicative conjunction. But on the other hand, we do want the disjunction to be additive, which is pretty weird. And in particular, you want the duality between them. So that makes the whole thing a bit tricky. You normally, at least I haven't seen any system presented in the literature where you have those properties mixed. In fact, I reckon that you already saw this talk, more or less. Right, exactly.
I've seen both Zach and Patrick Sherrard talk about logics like this, but I'm thrilled to get to see it. It's really good logic, and I really want to understand it.
Right.
I'm very happy this is a topic.
So okay, so it's a kind of an insane logic, and this, of course, these comes easily from proof by cases. So I'm having a reasonable introduction proof for the arrow as well. So you can see that those two things normally would be just dual to each other if you have in place like contraposition and a bunch of other principles. But in this case, question.
So it's about avoiding the conjunction principle.
So we want to refute this because it gives contraction.
Well, but it doesn't give contraction on its own. Right?
No, exactly. But in combination with the other principles. Yes.
Okay, and I'm wondering a bit about why the other principles are more important than this one.
Because this one that's a good question. I have no idea. The other ones are more important because in practice those are the ones that we're using.
Okay.
This just comes from our practice, let's say. Right? So it's just a logic built, sort of put together, let's say. In fact, you will see that some of the things I'm going to present, there might be some redundancies even there. There is no claim that this logic is, that the axioms are independent of each other or anything. It's just something that we just sort of put together and it does what we want. Right? And we want to introduce it to the rest of the world, let's say. So, okay, yes. So that's a novelty of this particular system. You have that weird interaction between those two things. And that kind of forces the semantics to be trivial in a sense. Because normally the usual algebras that you would look at to give semantics for substructural logic, they won't have these sort of weird properties because they would be full of algebras and stuff like that. And yeah, the way the way the operations interact in those algebras doesn't allow you to do this. Okay, yes. Let's see. So this is the logic is going to be called substructural dialectical logic. Maybe some would say dialectic logic, but I like the original Brady terminology, dialectical. And also I come from Cuba, so Marxism and everything. Yeah. So, okay, so as you can see, again, it's a totally ad hoc logic, more or less. So we just put a bunch of things together, so there you go. The log is through the middle. This we have a button in our language because we do want to be able to say that some things are absolutely false. Otherwise, again, you end up with in my mind, a silly language like LP or something like that, and then it's not clear that I can say that something is absolutely false, and yeah, that's very problematic. Certainly in mathematics. Some things you do want them to be absurd. Although Lewis is a proponent of trivialism and so on, so it might be that for him this is very counterintuitive. But yeah, for me it's the other way around. Trivialism I cannot really make sense of. So okay, and then of course some double negation elimination and introduction principles, the Morgan rules, what else? Some distribution rules as well. Yep. So, what else? What do we have? Okay, so the operational rules of the Gensen system. As you can see here, okay, some rules for disjunction. The rules for the arrow are pretty standard, nothing weird going on there. Actually, nothing weird going on here either. Right, just again, the interaction, some of the properties, the interactions between the conjunction and the disjunction, right? So this is not the way you would see it normally, given that those two things are going to be due to each other. Yeah.
What's on the left side of the sequence separator? Is that a list or a...
On the left?
A multiset or a...
Oh, yeah, sorry, yeah, I shouldn't clarify that. Yeah, all of these things are multisets, of course.
Multiset.
Because we are looking at a contraction-less system, so no contraction around.
But they're not lists, they're... Or they're not lists like Gensen used or finer structures, they really are multisets.
Multisets, yeah. Well, in fact, we are looking at finite multisets, but that might not be that important actually. Yes. So yeah, because in fact, so what we prove is weak completeness theorem. So for those purposes, this could be infinite, right? In the end, for the weak completeness theorem, it will just come down to finite multisets. But yeah, but this could be infinite, yes, probably. So, but I guess that in practice we never use an actually infinite.
I'm less worried about infinity and more about whether we can freely rearrange.
So you're talking about exchange. Yeah.
Or associativity, or right.
Let me see. If it doesn't appear here, then probably we can. Yeah, because we do have weakening. Yes, we should be able to do that. But yes, so
the reason I ask is the particular formulations of the rules you're using are the usual ones you see when exchange is absent.
Yes.
Which is fine if it's present, but you're taking all kinds of care.
Indeed. That's true. But in this case, I don't see why exchange in this particular context, but it might be dangerous, and it's good that, I mean, the reason why this was presented this way is because I wanted to do it in the safest way possible. So probably exchange is fine. But yeah, but let's keep it like this for now. But in fact, no, look, yeah, so this is the other thing. So since we have as an axiom, exchange is something that you would have to add actually, so it won't follow just from what we have here. But yes, it should be safe. I don't see a particular reason why that would be devastating, but still, yeah. And again, the structural rules will we have that weakening rule, and then we've got cut, that's it, no contraction or anything. So now let me give you a Hilbert version of this tracing system. which is 15 axioms. In fact, yeah, so here I might have added exchange here.
Yeah, 2, 3, 4, right? 2 and 3 are, well, 2, 3, 4 together are associativity and exchange.
Yeah, okay, yes. So in here, yeah, indeed, yes. So in fact, in the other side, you could have exchange as since it's a multiset, you can just exactly. So yeah, so okay, so we've got this bunch of axioms. Again, many of the initial sequence are just presented as axioms here. Again, the obligation principles, log exclude middle, counterexample, and so on. And okay, yes, the residuation law for this conjunction connective. So the conjunction connective is going to be residuating the arrow again. Oops. So yes, some distribution principles as well. Weakening in particular, we like weakening very much. That's something that you use all the time in mathematics as well. So okay, and of course, finally we've got most ponens. So this is the caveat here with this Hilbert system. We are looking at a Hilbert system where you've got multisets rather than sets of formulae. Okay, so the most ponens rule is presented in this way, involving multisets, and I'm gonna give you the definition of the divisibility for this particular system, right? So this is what makes it peculiar, but in fact it's not that peculiar. Some other people are doing work on this, in particular Francesco Paoli, Peter Cintula, and Tommaso Moraschini. They are doing some work, not exactly this, but something related to this. Basically looking at Gensen-style consequence relations and turning those into Hilbert-style consequence relations. And that's essentially what we are trying to do here. We are trying to externalize in a Hilbert system the internal consequence relation of a Gensen-style system. And okay, so the thing you need to take care with, the important new definition is when it comes to an application of most ponens, which essentially says, well, if I've got this multiset here, the way I can allow most ponens, an application of most ponens to happen is if I can split that multiset into sub-multisets, sort of. Such that from the first one we can deduce psi, and then from the second one we can deduce that psi implies phi. And as you can imagine, this is so. The idea behind this is that you will try to keep track of how many times. Again, this is to avoid contraction, of how many times you've used a particular formula, right? In a deduction. So that is what allows you to prove a deduction theorem. So we write. Yeah. So okay. So this is something that I already said. And then we have that the Hilbert system satisfies the deduction theorem in the standard form of a deduction theorem. But as you saw, the divisibility relation itself is not standard. So yeah, it depends on whether you want to say this is an improvement or not. For us, it's an improvement because the way we are thinking about this is we are not using, if we use one assumption once, we are not allowed to use it again unless it's a theorem. Okay? So that's a practical way to use this sort of system. And well, you can prove that it's equivalent to the Gensen system, right, provided exchange. Yeah. So yeah, so that's something. Now, the way you find semantics for this sort of system, as you can see, it's a very ad hoc system, motivated by real life, I would say. So, and we haven't been particularly picky in how we presented the system. So in fact, the semantics is sort of trivial. The idea is just to sort of give a proof theoretic semantics in a sense. Just look at, okay, so from the literature in substructural logic, there is something called Gensen matrices, which is used in the book by Hirakira Ono, Peter Jemsen, Nick Galatos, and Tomasz Kowalski, and they use this to as part of, okay, so something that has nothing to do with our purpose here. But the idea is that these Gensen matrices essentially mimic The way that you show that a given Gensen system is sound with respect to these Gensen matrices is because these creatures mimic the Gensen system. So they are just, imagine that you take the formulas of the Gensen system to be the collection of objects of your algebra. And then you take the connectives to be the operations. So you look just at the, say, a sort of Lindemann algebra of the Gensen system. And then the consequence relation, the internal consequence relation of the Gensen system, you define it in this new structure as holding even only if we have this sequence being provable in a sense. So let's say, right, so you have this universe of formula, let's say LA, right? And then you have all these connectives, right? 0 to Fn, plus you have this new relation that you introduce between the elements of this thing, in this creature. And then you say, well, look, one way to interpret this is saying, well, just send formulas to formulas and say that in this particular structure, two formulas hold, because the elements of this structure are just formulas, right? They hold, with this relation holds with respect to these two formulas, even only if this sequence is provable. In this case, this arrow is just the Gensen arrow, right? So it's not our arrow. So if this sequence is provable in the Gensen system, if this sequence is provable, then these two formulas are gonna, this relation is gonna hold with respect to these two formulas in this structure. Okay, sort of. And as you can see, that gives you a trivial kind of semantics for any Gensen system whatsoever. Okay, the only problem is finding that there is a structure like this, which is not the trivial one, because of course, if you just got this one, the Lindemann algebra, that's totally uninteresting, right? Yep.
But this isn't the Lindemann algebra, right? Because
no, this is not the Lindemann. No. So this part is the Lindemann algebra without equivalence, right? Without the quotient thing, right? It's a Lindemann algebra when you don't close under equivalence. Yeah. So, so in fact, you add this and then you get a semantics. So the burden of proof lies on essentially finding structures that satisfy this sort of description. I mean, again, of course, this particular structure for any given particular Gensen system needs to satisfy a bunch of principles in order for the Gensen system to be sound with respect to that particular class of structures. That's what we are gonna present. In particular here, you can restrict yourself to sort of finite multisets because we want to look at weak completeness. Completeness with respect to theorem hood. So yes, for compactness reasons that will suffice. Yeah, so don't get too scared by all of this weird notation. It's just so this is just an operation, and this is a homomorphism from the language into the elements of the not algebra, but yeah, an algebra plus a relation. Yeah, let's say. And yes, and you have one distinguished element that will represent bottom. 0 will be bottom, and then of course the result of applying this negation operation to 0 will be top. Okay. And yes, and then you can define that consequence relation model. So, okay, for instance, blah, 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 something. Okay, so there we go, the notion of validity, of course. Again, a sequence in the, a multiset in this case is going to be just finite, so this can be interpreted in this way, right? So you are looking at the elements, because these functions, of course, they are finitary, so they can only get finitely many inputs. And then, but that's going to suffice for the purpose of completeness. And actually, completeness is trivial. I already show you how to do it. So it's not. In fact, the reason why it's interesting that it's trivial is that, in fact, that argument you could just recreate it in the setting of this logic, and you could prove completeness using the logic without going to any sort of classical meta theory. Completeness. And probably soundness, because it's trivial enough. Now, there are some other things that I'm not so sure. I have the impression that they should also be proved this way, but it takes a lot of checking. And yes, that's work for another day. So, okay, so this is a bunch of principles that you need your structures to satisfy. It's just a rewriting of the principles you have from the Gensen system. Nothing surprising here. So you do that, and of course you're gonna get soundness sort of trivially as well. So this is why I'm saying that the completeness proof is actually something that you can do using this very same logic we are introducing. So, okay. So the Gensen system is complete with respect to the structures. And again, I already told you what the proof of completeness is. Look at this algebra that I constructed from the formulas, and they're gonna give you a counterexample to any known theorem to any known probable sequence of the Gensen system. So this is the part that I'm not sure that I can reproduce using this logic. Because it takes a lot of checking. We didn't do that. Proven 9 did it for us. Obviously, the idea is just to show that that sequence over there that we were worried about is not provable from the Gensen system, and it isn't. And this shows why. In particular, that's the reason, right? So that operation applied to 1, 1 gives 0, but 1 is not related to 0 in this way in our model, so that sequence fails. Whereas that structure is actually a model of the Gensen system that we presented. So in fact, there are, as you can see here, some non-trivial models of this thing. So the semantics at least makes sense. It's weird semantics, probably not super useful, but certainly useful for our purpose, which is to show to classical people that this logic makes sense, that we are not just working with something that in fact proves contraction, even though we are claiming it doesn't prove contraction. Okay, so that's one thing. Okay, again, we want to add, so this is the thing. So when it comes to identity and all of that, you get into trouble real quick if you have enough substitutivity. So we want to introduce an arrow to deal with the extensionality axiom, which is a relevant arrow that has much less principles than our stronger arrow would have. And it looks like that. And so we need to show that in fact adding this arrow to the system is indeed, it's a conservative extension of the original thing. And that's not so difficult to prove. The reason for that is that defining a conditional in this way, and not psi implies not phi, gives you all the principles you need and even more, right? So you can show that in fact adding that relevant arrow to the system won't let you prove any new theorems in the original restricted language that didn't have the relevant arrow. And with the relevant arrow, you can add extensionality in the Brady sort of way. Right? And we hope it's safe. This is the problem. We don't really have a non-triviality proof for the system. It's a very intricate system, as we can see. And the non-triviality, the proofs, the methods to show non-triviality available today are not super flexible. They are actually very limited in my mind. And in particular, you never get, or almost never you get any interaction between log excluded middle and weakening, let's say. If you even look at the work done by Hartley-Field and his collaborators on this topic, they've gone farther than anyone else has, as far as I know. And in their papers, you don't find a system that combines those sort of principles that we want to have around in this particular one. It would be lovely to find a non-triviality proof, open problem for anyone who wants to try it, but again, I want to publish, and that's going to take a long time. Okay, so how do we deal with quantifiers? How do we add quantifiers? The idea is just to do the same thing they do with cylindric algebras in first order logic. So it's well known that cylindric algebras, cylindric Boolean algebras, and so on, those creatures give you an algebraic semantics for first order logic. And the idea is that there are these operations of cylindrification which you can use to interpret quantifiers. And by a quantifier in this case, we are looking at something where, let's say, the universal quantifier, and it's quantifying a particular variable. Okay. So that's why we are going to have a bunch of indices here for these operations. These operations are going to be sort of representing the quantifiers, right? Relativized to a particular variable. And we already got countably many variables in our language, so yeah, not such a big deal. And yeah, so you need a function that keeps track of which variables are bound and whatnot, which is this function f, okay? And what you wanna, the restrictions you wanna impose on these creatures are essentially the same as before, plus a couple of more restrictions in order to deal with the quantification rules. Nothing surprising. You can sort of imagine what's coming next. So this is how to interpret, how to use these modes to interpret a quantification language. In particular, you need to restrict yourself to elements such as, to models such as every two elements of omega, the collection of every two elements of omega is the image of some element of U. U is a domain of values for the formulas of your language that we are looking at. So that happens because we want to be able to interpret these relation symbols. In this case, if we are looking at the restricted examples, we only have like 1 second two-place relation symbol. And what we want to do is that we want to say, well, the value of that is going to be some preimage of ij, right? So, and we know that there's going to be some preimage of ij because we are restricting ourselves to models where that is the case. And yes, so finally, of course, because of the way we introduce restrictions on our structures, those rules are going to be the ones that are satisfied, right? And you can sort of see where they come from if you pay attention, right? Recall that this is just a quantifier, sort of, right? So, and this is just the Gensen thing, internal consequence relation for the Gensen system. So you can see that there is an analogy there. And these things, of course, this is the other thing, right? So as you can see, there is a material conditional here because these conditions are given in a classical language. This is the classical part, again, finding counting models and so on. So what we are trying to just do is say that this thing right here, it's gonna just be interpreted as a material condition, right? So if this happens in the structures, in the sort of algebraic structures that we've got, then that's going to happen as well. And that's it. Many thanks for your attention.
David and then Thomas and there is.
Yeah, so if you take the conditional that you mostly focused on,
yep.
And you consider the biconditional formed from that,
yep.
Right? You can't, even if you have a provable biconditional, you can't substitute one for the other in general. What about the relevant conditional that you define?
That one could substitute.
You can substitute.
Probably, but it's extremely difficult to find one of those. I mean, to prove one of those.
Sure, but what I'm wondering is if there's some way to use that to get a non-trivial algebraic model of the sort you're after that is closer to a usual Lindenbaum algebra, right? That actually, that really does quotient. It's not just the formulas again, but that doesn't quotient away anything that ever matters.
Ah, I see.
Right?
I see
so
what you mean.
It doesn't go all the way down to your 4-element thing, right?
I see what you mean.
But it might be in the end. But when you say it's very difficult to get, it might be in the end that quotienting by it.
No, but
that it's not actually right. That if everything is every formula is in a cell by itself, and so there's
no. The quotient is difficult to get. The relevant arrow is difficult to get. Yes, because it's difficult in general to prove.
Non-trivial relevant biconditionals like unit distribution.
Yes.
Okay.
Some principles. Yes.
Not just the formulas. Again.
Indeed.
Okay. So yeah. So but if you can substitute along that, then won't that give you something more like a Lindenbaum algebra?
Yeah, certainly. But then again, I'm not sure why we want that. Because here the intention was just to show these models, they were presented just to show that contraction doesn't follow, right? To give you that counter model more or less. So, and in particular, that completeness theorem that I gave you was with respect to just a fragment that didn't contain the relevant arrow. The relevant arrow can be added conservatively, but the work of showing a semantics further relevant arrow as well. That's a different thing. Yes, and we can do it. I presume it's not going to be difficult. And certainly, yes, you could probably build a proper Lindemann algebra in that sense. But then again, it's not exactly Lindemann algebra because you've got the relation. So once you've got the relation, structure. It's like phase semantics from the book by Reston. So yeah, that's it.
So great talk. When you presented the sequent calculus, one thing that was striking is that when you presented the operational rules, there's no negation.
Yes,
right?
no negation.
Essentially, it looks on its face that you are sort of following in Nelson's footsteps here, because what you've sort of got is with Nelson, right? The de Morgan's laws don't follow from any inherent properties of disjunction or conjunction. It's just that this is a way to disguise, right, a conjunction as a negated disjunction and so forth. It's essentially a positive logic, right? They just disguise or encode everything through the language of negation. I don't know if that's entirely the case for your stuff, but it certainly is suggestive.
Indeed, it should be, right? Because the only negation principles are introduced as initial sequence.
Yeah.
So there are no operational rules for negation, other than what you could derive, let's say, using the rules for, since these consequence relation, since the arrow introduces and so on, so you could probably derive some derived operational rules, more or less. But yes.
So if I understood you correctly, one of the sort of things to do here is to find it better semantics.
That would be good, yes. Better semantics would be good.
I think that given the proximity to the Nelson stuff, that really taking a look at the Nelson, the twist structures and all those sorts of things, or looking at creating both a verification and falsification condition for each thing, I think that might give you an edge when you're looking at these things. Because you might find that a lot of pre-existing semantics, if you treat them as sort of a positive semantics and then just sort of sneak in the negation on top of them, that might pop up and just correspond to this.
That's an interesting thought, actually, yes. The other difficulty would be with the interaction between, again, the multiplicative part, the multiplicative conjunction.
That's the Nelson thing. Is that the Nelson? You look at like Heinrich's stuff for negated conditionals. He's got 4 different systems because it doesn't matter. The negation, the falsification conditions for any connective are entirely. It doesn't matter what your verification conditions are.
That's
right. It's entirely distinct. So in this case, it doesn't. There's nothing that supervenes in the properties of conjunction and disjunction that gets you to Morgan's. It's just by fiat.
Indeed.
And so you really, if you go that sort of looking at it in Nelson style, you don't need to establish any harmony between the connectives because you get it for free.
That's okay. That's cool. I didn't know that. To be honest, I haven't looked at Nelson's work. So
I'd suggest looking at twist algebras.
Twist algebra. So what's the paper? What's it?
I will get it for you. I will get you some.
Good. Thank you, Thomas.
Nice.
Luis?
Yeah, could you go back to the axioms? And
Wait a second.
I was wondering.
Some redundancy might be present here.
No,
okay.
That's not a problem. My concern is about the first one, the irrelevance.
The weakening, yeah.
And
But this is not a relevant arrow, right?
yeah,
This is a regular.
yeah, but even that way, doesn't it get you in trouble in the presence of the deduction theorem, contraposition, and double negation?
No, we don't have contraposition.
You don't.
That's a trick. No contraposition for this arrow. There is contraposition for the relevant arrow.
Okay.
But no contraposition for this. Otherwise, yes. Contraposition and the other stuff is a recipe for disaster, for sure. Hurricane Irma.
Really quick. So you did talk about sort of how we're supposed to interpret the relevant arrow, or at least because it's a relevant implication.
Exactly.
There. But you didn't really mention, other than this is a conditional, how to understand it, so that it meets certain criteria. I get that. But is there any sort of way that I'm supposed to understand this distinction to the relevant condition?
Indeed. So this we call this the deducibility conditional, right? The deducibility conditional, because it's let's say Yeah, it's trying to just give you the properties of the divisibility relation of the logic, as opposed to a relevant conditional, which is not that. That's why we would get a deduction theorem here. And that's why we have weakening as well, because that's something that you would get from that sort of thing. So yeah.
Yeah, in terms of prospects for non-triviality, so there's the way that goes through building recherche and complicated structures, and that people like me tearing our hair out, and then there's the route through cut elimination.
That's what gets people like me tearing their head.
Okay, but like, I mean, obviously I can't see all the details play out, but in terms of the sort of, I mean, obviously the Gensen system you gave is not designed around cut elimination. It's designed to depend very heavily on cut.
Indeed.
Do you think there would be, let's just think about the logic, right, which is of course going to be non-trivial.
Yeah.
But like, do you think there are prospects for reasonably straightforwardly generating a cut-free system for this logic?
I don't, because of the following reason.
Yeah, what goes?
Let's say I've looked let's say Elias Sadini's proof. He's got this logic.
But he's got all kinds of stuff you don't have to worry about.
Yeah, but it's the problem. I've got a bunch of stuff he doesn't have to worry about, namely all these initial sequence.
No, but like, look, you'd have to get rid of these, but there are really straightforward ways of turning these things into rules based on the Negri von Plato stuff that you mentioned earlier today.
Okay.
And you can turn this stuff into rules without much trouble. As long as you
without bringing back those things I don't want to bring back.
I don't see why not. Right?
Okay.
So you would take the kind of Avron style, right? You give rules. I mean, it's again the Nelson stuff, right?
Yeah, I was gonna say, if you look at the Nelson calculus,
yeah, like. So I look at this and I don't see any trouble for turning it into a cut-free calculus, except maybe the counterexample principle, which is a little weird to me.
That's weird. Zach loves that.
Oh, look, I'm sure it's useful, right? But I'm thinking in terms of designing a cut-free system.
It is very useful.
But like, I was wondering if you had found, in fact, there are difficulties making a cut-free system here.
I mean, I didn't try this route you're mentioning, so I did find that there were difficulties when it comes to all of these initial things.
Sure, no, and this is not a cut-free system. But let's play with it, right? Because the first step to non-triviality by cut elimination is just getting cut elimination for the logic.
Indeed. And that's where I had trouble.
Okay, sweet.
But certainly, that would be one thing to look at, actually, because I didn't think about formulating this in an alternative sort of way. I will.
Yeah, I mean, I have ideas for things to try, but of course, you never know whether it works until you actually do it.
Yeah, I mean, and to be honest, my knowledge of proof theory is fairly limited, and it comes from Ono Sankowalski's book and stuff like that, which is pretty much for substructural logic and pretty standard.
But they're going to be assuming things that you can't work on.
Indeed, exactly.
But I do think if we take the sort of Avron style look under negation to the next connective sort of stuff, all of this.
So you're talking about hypersequence?
No. The kind of system that he gave for FD, or like JC's system for FD that takes up on this, right? So the idea is you give rules for conjunction, rules for disjunction, rules for implication.
Okay.
And separately, no rules for negation alone, but rules for negation that look one connective under it. So you give rules for negated negations, rules for negated conjunctions, rules for negated disjunctions, rules for negated implications. And just like in the model theoretic side that Thomas was saying, these can be totally independent. Similarly on the proof theoretic side, they can be totally independent.
if you look at your double negation axiom, and you just think about having an operational rule for double negation, it's immediately apparent how you can turn that into a rule.
Yeah.
And then just lift that to the other cases as well.
Okay.
Yeah, distribution, I don't know about. That could get fun. Counterexample, I don't know about. That could get
Distribution normally gets fun. Complexity.
But maybe we need to do the Dunn-Mintz two kinds of formula separators. You know, the sort of bunched kind of stuff. Anyway.
Right.
Okay, but.
That's
fair on the proof theoretic side.
Good. It's just that for me, proof theory is so mechanical. I don't know. Exactly. But that's the problem, right? Because it's so many. Check this case. There is no intuitions, no real things that can touch.
It's so much better than like nested transfinite.
But that's real things.
Let's keep it finite.
But that's real.
I'm with you.
Right. Thomas knows what I'm talking about.
Together.
Yeah. Yeah, but admittedly, this is a pretty nasty system, although extremely useful. On the other hand, you're welcome to try it. Yeah.
I kind of want to try.
You want to try it?
Now I'm really excited.
Yeah, I mean, about half of it is obvious, and then the other half is going to be fun.
Any other comments, questions, suggestions, bibliographic references? Let's thank our